Hey guys, so I'm back with another video. And again, I'm trying to do this whiteboard thing. I think it worked pretty well last time, so I'm gonna stick with this. But this week I am gonna start off by doing some more questions from 2.3 and sort of going through those. And I'll start off with one that I thought was really interesting and one that I had to get definitely some help on because I thought it was pretty tricky. But that so basically here's your problem. So you've got matrix A. Oh, trackpad. Okay. So you've got matrix A, which is of the form A, B, B, negative A. Now, we should remember that that's a reflection matrix. So make sure to keep that in mind. That should be familiar. Where obviously A squared plus B squared is 1. It's another part of that whole reflection thing that we've talked about. And I don't need that. So what we're trying to do is we're trying to find two non-zero perpendicular vectors, V and W, such that A times vector V is vector V, and A times vector W is negative vector W. Okay, so now that we've got figured out, we need to figure out what these two non-zero perpendicular vectors are. So first I'm going to draw a little image. So here we've got like a line L, right? I'm going to switch colors. So we've got vector V and then vector W. So V is the one on the line and W is the one perpendicular. Right? So we want to find these vectors. Well, there are two ways that we can do this, right? One method is super simple. You say A, B, B, negative A times X, Y equals XY. And that's for V. And then for W, you say A, B, B, negative A times, we're just going to say WT for the vector W equals, you guessed it, negative W, negative T. And then you would solve. And here's the downside of this. So, I mean, it'd be pretty easy. You just, ignore this XY and this WT, and you would set A, B, B, negative A, and XY. You'd make that a matrix and solve. And you do A, B, B, negative A, negative W, negative T, set that into a matrix and solve. And you go about your normal elimination, what we know to do with matrices. And that'd be fine. But it'd also be pretty painstaking. It's numbers we don't know, so we can't put it into a calculator. And I mean, back in the beginning of this independent study, it was good practice. But at this point, we can kind of think beyond that and try to be a little bit more efficient. So another way we could do this is think about this a little bit more theoretically. So let's say that let's think about matrix V for a minute, or vector V. It's equal to XY. But we also know something else. We know that A times vector V is vector V. So we know that this X is going to be equal to the output, right? It's going to be equal to what we get once we put X into the equation AX, right? And we know the same is true for Y. And we can say that, we can transform this a little bit, the way that we write this. But we want to write it in terms of A and B, because that's actually what the problem says. They want us to keep everything in terms of A and B. So what we can say here is that the vector x is also equal to f of A, B, and g of A, comma, B. And this A, comma, B is just a stand-in for the matrix, right? But like what we can say is that, you know, V is going to be the exact same thing as the output is really what this is saying, right? And we can just keep it in this form because that keeps it, that puts it right there in AB form, right? And that's going to be useful because what we're going to do is we're going to use the dot product. And you might ask how. Well, let's move over to think about W for a second. Because we're going to keep W right now in the form of WT. Right? We're just going to keep it that way. And you'll figure out why in a minute. But here's what we can say. Because if we multiply these two things together, it should equal 0, right? Why is that true? I mean, you probably already figured this out by now, but they're perpendicular, right? And we know that when things are perpendicular, if you multiply them together, they get 0. So let's figure out how we would do the dot product for this. Because if we were to dot this, we would have f of AB times W plus G of AB times T equals 0. Let me make this a little more obvious if that isn't F. Okay. So now that we know this, let's think about what we need to figure out. So we've already got the vector for V in terms of AB. We need to figure out the vector for W in terms of AB, right? So let's solve for W, right? Let's just figure out what W is going to be. So if we did that, we could subtract G of A, B times T. And so we get F of AB times W is equal to negative G of AB times T. And the last thing that we do is we would divide F of AB on both sides. And so we'd end up with W equals negative G of AB T over F of AB. Now, here's what we need to figure out because we know what W is, right? And we have that in terms of AB, but we've got this T right here. You've got this like pesky little T. But here's what you have to realize. T can be anything. And the reason why is because if we think about a vector, you know, vector is on a line, right? So if we've got a line and it's an infinite line, you know, at some point it's going to reach every single Y value. And at some point it's going to reach every single X value. That's the definition of a line. What really matters is like the ratio, right? It matters that you've got the right X going with the right Y, if that makes sense, right? So let's say that we set T, which is our Y here, equal to anything. We can make it 1, we can make it 4, we can make it whatever we want. Well, if we do that and then we plug that number into this equation for W, well, what are we going to get? We're going to get the right X value that corresponds with the correct Y for that line, right? So really all that matters is that you've got like one of these things defined and then the other one doesn't matter. You can plug in anything because it'll equal out to be something on that line. So that means that we can just sort of pick, if we want to draw this matrix in here, we can just sort of pick something for T. So let's pick the easiest thing. We're going to say that T is 1. Well, that means that our matrix for vector W, or that our vector for vector W is going to be negative G of A, comma B divided by F of A, comma B, 1. Let's think about that. We've got two vectors now defined in terms of A and B. We've got the one that is parallel, that is defined in terms of F of A, comma B, and G of A, comma B, because as we know, it's parallel, so the input equals the output. And we took that and we used the dot product, we shifted some things over. And what we figured out is that we can write W, not the vector W, but the component of the vector W in terms of F of AB and G of AB. And then from there, we can pick any number for T. And what we get is two matrices that are two vectors that are written in the form AB. And that would be how you would write this from this line. But of course, as I said, you could do it this other way. You could do it this very simple way. But well, one, I would say that the math is really pretty here and really cool and logical, which I love. But also it saves a lot of time and a lot of grunt work of having to shift everything over, work on eliminations, etc. So I thought that was really cool. And let's see, I can erase that now. No, that's not an eraser. That's an eraser. So the next thing that I want to do is, I believe, another theoretical example. Actually, no, I wanted to clarify a little bit about the identity matrix, if I remember correctly. Because when I was doing my problems last week, I forgot both what an identity matrix is and what a transition matrix is. And it's been a little while, so I think those are important definitions to have because they can definitely make things easier. Then they show up a lot in problems. They're really useful for proofs. They're definitely, identity matrix is definitely really useful for inverse, as I kind of already, we've kind of already used it before. But yes. Feel a little bit like the Khan Academy person doing these videos with this whiteboard. Okay. All right. That was painstaking, but we're good. So the next thing that I wanted to draw our attention to is, and let me just, I've got a helpful Google Doc somewhere around here. Okay, so the next thing I want to draw attention to is this idea of the identity matrix, and specifically, once I get to the problem, an identity matrix where you're trying to kind of work backwards. And I'll show you what I mean by that, because it's quite useful. And I think I definitely need to clarify it, because if it confused me, it's probably confusing you. So, okay. So if we're trying to figure out the matrix X. And we've got X being multiplied by this matrix 1, 2, 3, 5. And you do that, you get this thing I2. I'm not sure if I've used this notation before, but what I2 is the identity matrix in the subspace of 2. And if I remind you, the identity matrix is when you've got 1, 0, 0, 1. And of course, there might be more components, but like I said, this is an I2, so it's a 2 by 2 matrix. So if we're trying to do that, then it's really quite simple. From here, we just set 1, 2, 3, 5 equal to 1, 0, 0, 1. And here's the thing, I'm not going to take us through this work because we obviously know how to do that. And in fact, you can put this into your calculator. You can put it into your calculator really, really simply. And there's like a whole series of steps you can find on the internet for how to do that. It's really, really simple. So I don't need to do that. but I just want to recognize that what is this matrix X then? If we're multiplying the original matrix times the identity matrix, or having it equal the identity matrix, then what's that going to be? Well, it's going to be the inverse, right? Like we've already sort of established that. So that means that matrix X is the inverse of 1, 2, 3, 5. That was really, really fast. I just wanted to kind of remind everybody of that because it definitely confused me. Okay, the next thing that we're going to do is, yes, number 43. This one is, I think, really useful for looking at how geometry can intersect with linear algebra. And in fact, Dr. Prudham and I were talking this week when we were meeting about how linear algebra is really a cool way to connect like everything that you know in math. You have calculus and you have multivariable calculus and you have algebra and you have pre-cal and you have geometry and trig and all of these things, and they all come together in this really, really beautiful way. This is a really good example of geometry. I really, really liked it. So, page. Okay. So, this one is number 43 of the in the book, and you've got this problem. We've coming back to that L shape that we love so much. And you're given a vector X, surprise, surprise, a line P, and a line Q. And you're told that this right here is 30 degrees. Okay, so we're going to do a series of reflections because what they say is that we're considering the linear transformation of T of X equals Q, reflection of Q times reflection of P of X. So in other words, we first reflect X about P and then reflect that about Q. So if that's true, let's think first. We reflect X about P. Well, that's going to be kind of like that, right? It's going to be, I'll draw this a little bit better. It's going to be like that line, right? And then if we reflect that about Q, it's going to be like that line, right? And what they want us to know is they want us to figure out the angle that, so they want us to figure out the angle that between the, they want to figure out the angle that the vectors T and that the vectors X and T of X enclose. Let's think about this. Because if we get rid of this thing right in the center, the angle is going to be this plus this, right? We need to figure out what these two things are, right? Well, how can we do that? Here's what you need to remember about a reflection. You probably remember this from geometry. It's going to be symmetrical, right? Like this angle is going to equal this angle, right? Because it's reflected about this line. Well, if we know that this is 30 degrees, and if we know that these two are symmetrical and these two are symmetrical, well, then that means that this is going to be split in half, right? Because what we know here is we've got 30 degrees, right? And if it's splitting, so if it's splitting everything in half, right? Then that means that we've got this, this, so two thetas, right? These are both theta, and two phis. But here's what we know. We know that phi plus theta equals, well, what does it equal? 30. Well, what is this? This is phi plus theta. So this angle altogether is gonna be 30 degrees. And so that's going to be your answer. It's going to be 30 degrees, just like the same as in here. And this I thought was really, really useful to do like a little bit of a refresher of geometry and realize how you can use really simple geometric facts to figure out relationships between vectors. And I thought that was helpful. A lot of these things, I think, with linear algebra, it's a lot of creative math. A lot of the times I'll go to Dr. Prudhomme and I won't have gotten something. And when he explains it, it makes perfect sense. But it's kind of just learning how to think in that way. Learning so many different options and so many different proofs and theorems and everything that you've learned over the course of your math career to figure out what's going to be most useful. Which I think is really cool. Okay, the next one that I'm going to do is coming back to that web example. We've done this example several times now. We've got the web pages and the links and like people switching between them. And I'll just draw it again. Okay. So this particular problem basically wanted you to find pages I and page J such that it's impossible to get from page J to page I. Can't happen by following 4 consecutive links. In other words, follow the links 4 times from starting at page J, and you can't end up at page I. It's impossible. So this is fairly simple. Like this part is very logical. The numbers that I got were J is 2 and I is 4. That part's really simple. And I can show you that too, because if you start out at 2, well, you take the first link, which means that you can go here, or you can go here. So you take the second link, which means that you can go here, or you can go here. You can also technically go back to here. You take the third link, which means that you can go here, or you can go here, or you can go back here, or you can go down here. And you take the last link, and you up here, or here, or here, or here. You can't end up at 4. Now you hit 4 on one of those times, but you don't land on 4. You can't possibly land on 4. And that's just, looking at things and puzzling it out, and that's fine. But what's, I think, helpful to connect this back to an idea of powers of matrices, something that we explored in the last lesson, is the book asks, what does this actually say about the matrix that you've got going on here? And what it says is that you've got this matrix A to the 4th, right? What it says is that row 4, 1, 2, 3, 4. So row 4 of the matrix A4 will have the second column as 0. Let's think about why this is. Because the idea is that this side, this is kind of like your outputs, and these are your inputs. Well, if your input is 2, right, that's going to be this second column. And if your output is 4, it's going to be right here. And it's got to be 0 because there is no portion of J2 of people who start at 2 who end up at 4, right? For the 4th power matrix. And that I think is really useful to think about the differences like in how the matrix changes between different powers of matrices, because this number wasn't always 0, right? I mean, if it was just A to the 1 to get to 4, it was 0. But if you've got, let's see, A to 2, I mean, there was a portion because if you got A squared, there was a portion because 2 went down here for 1 and then over here for 2. right? So some people from 2 did end up at 4, but a to the 4th has gone back to being 0. So that I think is helpful just to kind of like visualize and think about the powers of matrices a little bit more, because I know it can be a little tricky to think about powers anyway, to really visualize that and have that in your head. I think once you get up into big numbers or a little more theoretical conceptual stuff, and I think this makes it a lot simpler. So yeah. All right. So our next one, we're going to say that A, here's our next problem, is a 3x3 transition matrix. Right? So we want to find the matrix product of 1, 1, 1 times A. So this is, I wanted to remind us of what a transition matrix is, because a transition matrix says that every single, so transition matrix says that every column or every row adds up to 1. Every row sums to 1, which is different than a, but if you think about that, you know, a transition matrix is also going to be, have every column sum up to 1 too, right? Because the rank is going to be equal to the number of rows. But that's true. Let's kind of draw this here. 1, 1, 1 times this 3x3 matrix, but we've got 1, 0, 0, 0, 1, 0. Right? So if that's true, what are we going to get? Well, if we think about this, if we multiply this by this row, and that row, that means we're going to end up with, we've got 1 times 1, 1, 1 times 0, 0, 1 times 0, 0. And you're adding these together, remember, because it's multiplication. And we're going to get 0 plus 1 plus 0, and 0 plus 0 plus 1. Well, what are we going to end up with? 1, 1, 1. So in other words, this is the same thing as that. So if you do 1, 1, 1 multiplied times the product times the transition matrix, you just end up with 1, 1, 1. I wanted to remind us of this because I sort of forgot what the transition matrix is and that sort of fact about it all adding up to 1. And that becomes really important for the proof. So it's really helpful to review those little facts like that because they really are kind of what you have to go on to figure out proofs on. Like the facts and the definitions of different types of matrices and vectors and relationships. And you kind of have to make sure you stay sharp on them because that's how you figure out proofs. Now, I think I have just one more example, and I found it to be, I think, really interesting because it was a proof. It was, I think, a really interesting and kind of pretty. So, I am not much mistaken. We're going to be talking about equilibrium vectors. Yes, we are. Okay. So I know we did equilibrium vectors a little bit, but they're useful to review again, definitely. So we're basically what they want us to use is the proof that we already have for equilibrium vectors. They want us to prove part of it that we didn't in the lesson. And what they want us to do is they want us to prove that because we know that the limit as m approaches infinity of a to the m times vector x equals this distribution, this equilibrium vector. They want us to use that fact and prove the next part of the theorem, which is that the limit as m approaches infinity of matrix A to the m is equal to this. The columns are the equilibrium vector. So basically, here's how we're going to prove this. We're going to set, oh, sorry, that times vector x. So what we can do, and I'm going to switch to different pen color, is we can set this set it equal to the other part of the theorem, and then solve from there. Is equal to the equilibrium vector. So first of all, let's think about this, because here's what we can think about. We know that this, the equilibrium vector, is going to be equal to the sum of the component 1, component 2, or not the sum, sorry, but it's going to be equal to component 1, component 2, all the way up to equilibrium component n. Right? Another way that we can write this that makes it really simple is using the sigma sum. So the equilibrium vector x is going to be equal to the sigma sum of, as I equals 1, it goes all the way up to I equals n. It's going to be equal to 1, right? Because this is here where we use a really important fact, which is that these are all distribution vectors, right? And what we know about distribution vectors is they all add up to 1. And that's kind of the fact that we have to base all of this on. So the equilibrium distribution is basically what we just said, equals 1 when you all those components sum together. We use sigma sum notation. Then we can say the same thing about vector x, because it is also, it's the initial distribution, but it's still a distribution vector, which means that x1, x2, all the way up to xn can also be summed. So where we say the sigma sum as I equals 1 all the way up to n of x equals 1. We've got these two sigma sums. So we can rewrite this first part knowing that. So we can rewrite is that we've got EQ1, EQ2, all the way up to EQN. And then we just keep going. We've got EQ. This would be and then we keep going. I'm not doing a great job of labeling them because I think it's a little necessary. I mean, it's necessary for true proof, but I'm just kind of trying to show you this. But then we would have that multiplied times x1, x2, all the way up to xn. And then if we multiply these two things together, what would we get? Well, we would get, let's write it in terms of sigma sums. The sum of EQ I times x, EQ1 times x1 until they both equal n. Then we get the sum of EQ2 times x2 until they equal n. And EQ n x I, right, x n. And that's the way that you write this multiplication. Now, we can pull out, see, if we've got the sigma sum, what we can do is we can pull out the EQ1, EQ2, EQN thing. And the reason why is because we've got the sigma sum applying to both of them. And so we can sort of pull one out. We can say, oops, I'm writing this very poorly. Sorry, this should be xi. These should all be xi's. Okay, now here's the important part, because how do we prove? What we're trying to prove is that this whole thing is equal to like EQ1, EQ2, all the way up to EQN, because that's what the distribution vector is, right? So the easy thing to say is that if we've pulled this out, if we've made these sigma sums, well, these sigma sums of x's have to equal 1, right? Because of what we said about the distribution vector. So if we cross this out and write 1, cross this out and write 1, and cross this out and write 1, EQ1 times 1 is going to be 1, EQ2 times 1 is going to be EQ2, EQ3 times 1 is going to be EQ3. So in other words, it's just going to equal this, which is the equilibrium distribution vector. So that is kind of how you prove that. You set these two things equal to each other, and then you kind of go from there. You break it down into its component parts. You use sums. You use the idea the distribution vectors all add up to 1, and you can use that to prove what you need to prove, which is that these two things are equal to each other. And I thought that was very cool. I'm going to stop the video here. And I'm going to come back and we're going to talk a little bit about 2.4, which is a fairly short chapter, should not be too bad.